Hello everyone. Today we are going to start with the second unit of physics, that is light. The first chapter of the second unit is refraction of light at plane surfaces. Now let's understand the meaning of the word refraction. So before going to the word refraction, I would want you to remember that in the ninth class last year, the this, I think in eighth also you studied about light, reflection, refraction both. But still, in the ninth class, you've studied one chapter which was about plane and spherical mirrors. And in that chapter, we studied a very important term, which is reflection. Reflection. What is reflection? Reflection means the phenomena of bouncing back. The phenomena of bouncing back of light after striking a surface into the same medium. Okay, so let's understand how does that happen. Okay, uh, I want all of you to take some notes because that is important. So be ready to take notes. Okay, so suppose this is a surface. This is a hard surface. Maybe this is a mirror. You know how to represent a mirror? A mirror is represented as a line, and on the one side of line there is silvered surface, that is non-reflecting surface. Okay, like these zigzags. Okay, so this is basically a mirror. Now on this mirror, a ray of light will strike. If a ray of light will strike on this mirror at any point, let's say it strikes this point, it strikes this point. Okay, it strikes this point. So you know what is this ray known as? This ray is known as incident ray. Incident ray. Okay, so this ray, let's name it ray A O. Okay, ray AO is the incident ray. It strikes this surface. This surface has to be, this surface has to be opaque or non-transparent. So the ray of light cannot go inside. So light is thought of to be made up of these small rays. Okay, light, we can't call it that light is made up of rays. Maybe it is made up of waves also. It has a dual nature. But for clarity of our understanding, we'll think of light to be made up of these rays. Okay, so what next? After striking this hard surface at point O, where point O is point of point of incidence, point of incidence, what happens to this ray of light? This ray of light, this ray of light bounces back into the same medium from which it had come. It bounces back into the same medium. Okay, this is something unique, but just a moment. Yeah, now it's perfect. So I will draw one more ray such that it looks like it goes back into the same medium. So what is that medium we are talking about? Medium is this space. This space on the upper side of this reflecting surface. This is reflecting surface. Okay, so this space above the reflecting surface is known as medium. So this is incident ray AO, and OB is known as reflected ray, right? So an incident ray strikes a reflecting surface at the point of incidence, and bounces back into the same medium, which is supposed to be air over here. It can be anything, air, water, anything, any transparent medium. Okay, and it bounces back into the same medium. This whole phenomena is known as what? It is known as reflection. This whole phenomena is known as reflection. Why I'm telling you this is because in order to understand refraction, you must have a clear idea about reflection first, and then we can go to refraction. So what is reflection? Reflection is bouncing back of a light after striking a surface into the same medium. Now I want to just point out one more you can say important stuff which is related to the phenomena of reflection, and that is a little technical. We have studied it last year, but just for the sake of you can say clarity of the concept of refraction, just note this one. So there is this, you can say, this imaginary line. There is this imaginary line which is drawn at the point of incidence, which is perpendicular to the reflecting surface. So what is this imaginary line? This imaginary line is named as n n dash. n n dash. N dash I'm going to write over here. N dash, n n dash. And what is this n n dash? This n n dash is known as normal. Normal at the point of incidence. Normal at the point of incidence. So that normal which we have drawn, it is an imaginary line. Why have we drawn a normal in this case? Normal makes the whole idea of reflection for us to understand and to make it easier for us to understand. Okay, so what is this normal has to do with the process, or you can say the phenomena of reflection? I will tell you. Do you see this angle formed between angle of incidence and normal? This angle which is formed between angle of incidence, the incident ray and normal, is known as angle of incidence. I. What is I? I is known as angle of I is known as angle of incidence. What is angle of incidence? Angle of incidence is the angle formed between incident ray and normal. Angle of incidence I. Okay. Similarly, there is one more angle formed between normal and reflected ray. That is angle of reflection. So what is R? R is, let me write it here. R is angle of reflection. Angle of reflection. Okay. So this is what we had studied while studying reflection in class 9. Achha, and then there were some laws of reflection. Do you remember? Laws of reflection told us that the angle of incidence is always equal to the angle of reflection. I is equal to R. Angle I is equal to angle R. And incident ray, reflected ray, and normal, they all lie in the same plane. They all lie in the same plane. Okay. So this is what we studied in class 9, and this is very important to understand refraction. This is reflection, bouncing back of light after striking a surface into the same medium. But what is refraction? Let's study that now. Let's understand what is refraction. So the word refraction means that when it is a phenomena which happens when a ray of light a ray of light enters one transparent medium from another, when a ray of light enters one transparent medium from another transparent medium, it bends. It bends. This is the main part. It bends or changes its path. It bends or changes its path. When a ray of light enters one transparent medium from another transparent medium, it bends or it changes its path. It bends or it changes its path at the point of incidence. What is the point of incidence? We just saw at the point where it strikes that another, or the you can say the boundary of the boundary of separation of two medium. It bends or changes its path at the point of incidence, or you can say the boundary. Where is the point of incidence located? It is located at the boundary of boundary separating, I'm sorry, boundary separating two media. Media is plural of medium. Okay, so at the boundary separating two media, when this ray of light strikes that boundary, it bends, it changes its path. So when a ray of light enters from one transparent medium to another transparent medium, it bends. And this bending of ray of light is known as refraction. This bending of a ray of light is known as refraction. Okay, so this definition has been created or made by me impromptu just now, but this is technically sound definition. I am not let go of any of the core concept of refraction. Yeah, this might be a little different from your textbook definition, but to understand the concept of refraction, this definition is more than enough. What I can suggest you is, in your school exams or in your board exams, you write the definition which is written in the textbook word to word. But for understanding the concept, you can follow my definition of refraction. Okay, so this is what refraction is: bending of ray of light when it enters from one transparent medium to another. So how does it look like? And how is it different from the process or the phenomena of reflection? See, in reflection, the ray of light was not entering any medium. It was just bouncing back into the same medium after striking a surface. Okay, so that is the main difference. Here, the ray of light is not bouncing back. It is actually entering another transparent medium. And because it is entering from one transparent medium to another, it is changing its path. Let's understand how is this all things happening. Okay, let's understand with the diagram. Okay, so suppose this is a boundary separating two media. This red line is a boundary separating two media. Here there is air and here there is water. Air and water. Okay, let me draw a normal. First of all, I'm going to draw a normal. With a black line, I'll draw a normal. Okay. Okay, I'm sorry for that. Okay, so this is our normal. Normal is a imaginary perpendicular drawn at the point of incidence. Okay, here the normal is not limited to the point of incidence, but I have drawn the normal in air also and water also. So the boundary which is separating two media has this imaginary line on it which is perpendicular to the boundary, which is the normal. So this is our normal. Okay, let's call it n dash. n n dash. Okay, now let's draw incident ray. Okay, so where is this incident ray? Let's draw it from here. Sorry. Okay, there is one important word which I missed in the definition, which I just come to know, but it's okay. I'll tell you what is that. So this is the incident ray. A O. AO is the incident ray, which is striking the boundary separating two media. So this ray of light is entering one transparent medium to from another transparent medium obliquely. The word obliquely was missing. Obliquely means slant. You see, this ray of light is not entering straight. It is not entering normally. It is not entering along the normal. It is not perpendicular to the boundary separating two media. It is entering obliquely. It is entering slant. So whenever a ray of light enters from one transparent medium to another transparent medium obliquely, what happens to it? What happens to it? Let's see. I will make a reflected ray now. Refracted, I'm sorry, refracted ray. So what happens to this ray? This ray bends according to the definition which I just told you. It bends and it becomes OB, refracted ray. Do you see what is happening? This ray of light is entering from air to water, from one transparent medium to another transparent medium, and at the point of incidence, at the boundary surface separating two media, it bends, it changes its path. Originally this ray was going in which path? Originally it was going in this path. You see, this is the original path of the ray. Do I have a dotted line option over here? Okay, I don't. I think I'll make a dotted line. Uh, yeah, I think I'll just make a dotted line over here with some other color, maybe red color. So this all things they take time, but it's good for your understanding. That's why I don't. It doesn't matter that where I'm whether I'm taking time or whether I'm doing it quickly or whatever it is. But I want all of you to understand the concept very nicely. Okay, yeah. So as you can see over here, the dotted red line shows the original path of the ray. Do you see that? I will erase that for a moment, but if you want to take a note, please take a note. This is nothing but the original path of ray. So just imagine if there would have been no water, or you can say the second medium, then the ray of light would have traveled in this original path, in the direction of the original path. But because there is water, because there is another medium in its way, in the way of ray of light, what happens is it bends, it changes its path. This is refraction. This is what we are going to study in this chapter. Okay, so I want to give you few more you can say terminologies. What is AO over here? AO. AO is incident ray. What is OB? OB is refracted ray. What is NN dash? NN dash is normal. normal at the point of incidence. Okay, what is angle AON equal to? Sorry, what is angle AON equal to? Angle AON. Do you see angle AON? This is I. I is angle of incidence. I'm sorry. Angle of incidence. What is angle BON dash equal to? BON dash. It is angle of refraction. Okay, so these are the terminologies which we see. Angle of refraction is also given a symbol R. Okay, so these are the terminologies which we see. Okay, so now we can understand. Now we can understand what is basically happening in the whole process of you can say refraction. Okay, I'm going to give you one more example. I think maybe two more examples to study, to understand the whole process of refraction, and then we'll go to our textbook and we'll try to understand little theory part of refraction. This is, you can say, I'm trying to you can say demonstrate what refraction is, but we also have to study the theory part for writing the answers. That I will go to in a moment. Let me draw one more diagram for you. Okay, so this is the second case which I want to discuss about. In the first case, the ray of light was going from air to water. Okay, and we understood that how it bent on entering the uh, water at the boundary separating two media. In the second case, I'm going to show you something different which might interest you. Just have a look. The ray of light is now being incident from water and it is going out in the air. Very interesting case. This is case number 2. In case number 1, the ray of light was entering from air to water. In case number 2, the ray of light is entering from water to air. Okay. Still, many things are same. The light is, refracting. It is changing its path. It's bending at the boundary separating two media. Okay. Let's try to understand now what is the scenario. I will change a few names for our better understanding over here. Now AO will become the incident ray and OB will become the refracted ray. AO is incident ray, OB is refracted ray. Angle AON dash will become the angle of incidence. Angle BON will become the angle of refraction. And NN dash is the normal as usual. Right? So this is the second case which we are considering. If you want to understand what is the original path, what is the original path, I will show you. First, let me sketch the dotted line which is required to understand the original path of light. Okay, so this red dotted line which you see, which is the original path of incident ray, but now after entering from water to air, it has bent. And we have to understand that what is this, what is happening, what is this relation between bending. Okay, but before going there, I would want to show you one more example. And here I'm going to change certain things. Okay, okay, so here what I want to do is, I want to I'm sorry, I just want to remove this. Wait, let me take a small eraser, very small eraser, and just remove this line. Great. Okay, so I was able to remove that line. Now let's see what is happening. In this case, in the third scenario which I want to show you, I want to now shift the position of incident ray onto the normal. Okay. Also the refracted ray comes back to the normal. Now when does this happen? In these two cases, what is happening, just understand. The ray of light is entering from one transparent medium to another transparent medium. Normally, the ray of light is entering from one transparent medium to another transparent medium. Normally, this is the third case. Is there any bending? Is there any refraction happening? No, there is absolutely no refraction. There is absolutely no refraction. So again, I want to emphasize on the definition of refraction which I had written here. When a ray of light enters from one transparent medium to another transparent medium, obliquely it bends or changes its path at the point of incidence or the boundary separating two media, and this bending of ray of light is known as refraction. Okay, this is what I told you. In this definition, one word I clearly highlighted, which is obliquely. The ray of light should enter obliquely, that is slant. Okay, it should not enter normally or perpendicular. If it enters perpendicular, enters being perpendicular to the surface separating two media, then it will not bend, then no refraction will happen. So bending of light will not be evident or visible when the ray of light enters from one transparent media to other normally. Okay, so that is the third case I wanted to show. Now in these three cases, there are certain facts which we have to emphasize on. So in the first case, the fact which I want to tell you is, whenever a ray of light enters from rarer to denser medium, rarer to denser. So air is a rarer medium, rarer, R-A-R-E-R, rarer. Water is a denser medium. Now you must be thinking rarer and denser in terms of physical density. No, I'm not talking about physical density of these two medium. Water is definitely physically denser than air. But what I'm talking about over here is the optical density of the medium. I'm talking about optical density of the medium. The optical density of air, the optical density of air is lesser than the optical density of water. So what does this optical density means? Let me show you. Let me create some more space and show you. Talk about optical density. Let's talk about physical density first. So physical density, which you have studied in physics earlier, it gives you the ratio of mass per unit volume of a substance, how heavy an object is. So these kind of calculations, they help you to understand whether a substance will sink or float in water or in any liquid, right? So density is that parameter. But here we are not concerned with physical density. We are concerned with optical density. And what is optical density? So optical density is that parameter which tells you that in a particular medium how fast the light travels. It tells you about speed of light. It tells you about speed of light in a medium. It tells you about speed of light in a medium. If speed of light c, the symbol for speed of light is c, small c actually. Let me make a small c for you. Okay, if speed of light in a medium A, let's say, is greater than speed of light in another medium B. If speed of light in one medium is greater than speed of light in another medium, there are two mediums A and B, right? Then if the speed of light is greater in whichever medium, that medium is optically rarer. Okay, its optical density is less. So medium A has less optical density, and medium B has large optical density. And what does this mean? What does this mean? I'll tell you. This means that medium A, in which the speed of light is more, which has less optical density, is a rarer medium, optically rarer medium. And medium B, in which the speed of light is less, which has large optical density, is a denser medium. Medium B is a optically denser medium, or just denser medium will also do. Okay, so what we are trying to understand here is the concept of optical density, right? So medium A and medium B are compared with respect to their optical density if we happen to know in which medium the speed of light is faster and in which medium speed of light is slower. We can easily tell which is optically rarer and which is optically denser. Now, the mediums which we are considering here is, in the example which we are seeing, the mediums which we are considering here is air and water. Okay, so air is optically rarer and water is optically denser. Air is optically rarer and water is optically denser. Now, what do you mean by that? It means that in air the speed of light is more than water. So if you compare the optical density of air and water, air is optically rarer than water. Water is optically denser than air. So air is a rarer medium and water is a denser medium. We will come to know more about this optical density or rarer and denser medium in detail when we go ahead in this chapter. But because the concept should not be very strange for you, let me tell you the optical densities of few medium. Let me compare them for you. So i will arrange I will arrange some uh, transparent mediums. I will arrange transparent mediums in increasing order of their optical density for you. the transparent medium which we are going to always consider in this chapter. So I'm going to arrange these transparent medium in increasing order of their optical density. So the first transparent medium which I'm going to write is air or vacuum. Okay, so air or vacuum has the least optical density. That means the speed of light in air or vacuum is maximum, 3 into 10 raised to 8 meter per second precisely. Then comes water. Water has little more optical density than air or vacuum. That means the speed of light reduces as the light enters from air or vacuum to water. And then comes glass. Glass is a transparent medium which has optical density greater than water and of course greater than air or vacuum. It has the greatest optical density. That means the speed of light in glass or water is the least, right? So I have arranged these transparent mediums in increasing order of their optical density. So just remember this much for our discussions. And what are their actual optical densities, or you can say refractive index? Refractive index we have not studied yet. That's why I'm not talking about them. But that will come to know as the chapter proceeds ahead. For now, whenever I talk about rarer and denser medium, it should be very clear to you. Denser medium में speed of light कम होती है, rarer medium में speed of light ज़्यादा होती है. ठीक है? So one thing, coming back to our original discussion, one thing we now know is air is optically rarer and water is optically denser. Now I want you to focus on this one thing. What is happening to the ray of light when it is entering from a rarer to denser medium? Air to water, or we can say on as a general you can say example, what is happening to the ray of light when it enters from air to water? Whenever the ray of light is entering from air to water, rarer to denser medium, it bends towards the normal. It bends towards the normal. Okay, so I'm just going to make some space over here and shift this particular thing a little down. Okay, let me just shift the whole thing a little down. Okay, so let's see, let's understand. Whenever the ray of light enters from rarer to denser medium, ray of light enters from rarer to denser medium, it bends towards normal. You see here, the ray of light is, the original path of ray of light was this red dotted line. But the final path is now shifted towards the normal. Normal is this black imaginary line. Okay. One more thing to notice whenever a ray of light enters from rarer to denser medium is that the angle of incidence is greater than, angle of incidence is greater than angle of refraction, angle of refraction. And this happens only when the ray of light is traveling from rarer to denser medium. What happens? The ray of light enters from, when ray of light enters from rarer to denser medium, it bends towards the normal and the angle of incidence is always greater than angle of refraction. Right? On the contrary, so after understanding what is refraction and when does it take place and how does it take place, we have understood one very important characteristic or property of refraction, that when a ray of light enters obliquely from rarer medium to denser medium, it bends towards the normal, or angle of incidence is greater than the angle of refraction. But let's have a look at the second case. In the second case, the ray of light is entering from water to air. So water being the denser medium and air being the rarer medium, we can say that the ray of light is entering from denser medium to rarer medium, exactly opposite of what was happening in the first case. Now the ray of light is entering from water to air. And what is happening to it? It is going from A to O, and then from O, it should actually, its original path is this dotted red line, but it is not going there. It is going away from that line and away, further away from normal. So it bends away from normal. It bends away from normal. When it enters from denser to rarer medium, the ray of light bends away from the normal. And one more important thing over here, angle of incidence, that is the angle formed between the incident ray, this is the incident ray AO, and normal, and angle of incidence is smaller than angle of refraction, exactly opposite of what was happening before, right? So these are, you can say, two more most important characteristics when you are studying refraction of light. Now, let us use our idea and our knowledge, what we have acquired here about so many things, rarer medium, denser medium, and bending away or towards the normal, or angle of incidence and refraction being not equal to each other. Someone is always greater than the other. But now let's put this, the whole idea of this refraction into the third category and understand what is happening over here. When the ray of light is entering from air to water or water to air, normally, that is not obliquely but perpendicularly, does it bend? No, it does not bend. In this case, can you tell me what is the angle of incidence? Angle of incidence is it 90 degree? If you're telling 90 degree, no, it is not 90 degree. It is how much? It is 0 degree. What is the angle of refraction? It is also 0 degree, and therefore we can say that incidence angle of incidence is equal to angle of refraction when a ray of light enters normally or perpendicularly from one transparent medium to another. Okay, so when a ray of light enters normally from one transparent medium to another, does not matter whether it enters from rarer to denser medium or denser to rarer medium. It does not matter. It does not matter whether it enters from rarer to denser medium or denser to rarer medium. When it enters from one transparent medium to another, normally it does not change its path. So refraction does not happen. Yeah, definitely the speed of light will increase or decrease, but it will not bend. And the angle of incidence will be equal to the angle of refraction, and both will be equal to how much? 0 degree. Both will be equal to 0 degree. Understood this thing? So now you know so many things about refraction. You have a, you can say, let me zoom out and show you. You can say you have a broader picture of the whole concept of refraction. We have to still go deeper, but if you compared with your earlier knowledge of refraction, you have now so much of knowledge. First we started with what was reflection, right? Then we understood the meaning of refraction, all the three cases we saw, right? We understood what was incident ray, refracted ray, angle of incidence, angle of refraction, normal at the point of incidence. We understood uh, what was optical density and how different it is from physical density, right? Then we understood about the characteristics which the ray of light exhibits when it enters from one transparent medium to another. Correct? So these all things we have learned in up to now. Okay, now let's go ahead and uh, uh, let me give you few more informations which I think they are must for you to understand refraction completely. Let me give you those. Okay, so the next thing which we have to study, I hope that you're taking notes, because these are like impeccable notes which I'm making live for you, right? If you take notes while I'm teaching you, any damn question you can take on, okay, you can answer, and that too in technical terms. We'll definitely go to textbook. I'm not hurrying to go to the textbook. First, let me share the knowledge how it should be in the sequence which it should be. Okay, so the next topic is, because we have understood what is refraction, laws of refraction. Laws of refraction. The first law of refraction states that sine of angle of incidence upon sine of angle of refraction is always a constant number without any units. Sine of angle of incidence upon sine of angle of refraction. You all know what is sine now, because you know trigonometry, right? So sine of angle of incidence upon sine of angle of refraction, the ratio of sine of angle of incidence to the sine of angle of refraction is always constant, and it is known as the refractive index. It is known as the refractive index of medium 1 with respect to medium 2. It is known as the refractive index of medium 1 with respect to medium 2. Okay, so this is the first law of refraction. What is the second law of refraction? Incident ray refracted ray and normal at the point of incidence all lie in the same plane. Incident ray, refracted ray, and the normal at the point of incidence, they all lie in the same plane. Now, this second law is very much, you can say, similar to the second law of reflection. There was, it's just one difference is there was reflected ray in that, the laws of reflection. Here it is refracted ray. But the first law is entirely different, and we need to talk a lot about this first law. Okay, so let me highlight this part by giving you an example. So we have our two laws of reflection, and the first one says that sine of angle of incidence upon sine of angle of refraction is a constant number, is always a constant number, and this, which is known as refractive index of medium 1 with respect to medium 2. Okay, now let's go here and copy this first diagram and take it over here. Right, so here few things I'm going to just delete. Okay, this is what refraction looks like. This is what refraction is. This is what refraction is refraction is bending of ray of light. Now here, can you see the angle of incidence? I, right? Can you see angle of refraction? R, right? Correct. Here, what they mean to say is the refractive index. Okay, the refractive index. I'm just explaining the first law of refraction, so please understand the refractive index of medium, the refractive index of medium 1 with respect to medium 2 is sine of angle of incidence upon sine of angle of refraction, sine I upon sine R. Refractive index of medium 1 with respect to medium 2. Okay, so there is this small mistake I have made. Let me correct it. First, let me tell you that here the medium 1 is that medium from which the ray of light is entering, and medium 2 is that medium in which the ray of light is entering. So ray of light is entering from medium 1 to medium 2. So here the small change which I was talking about is over here. The numbers in the subscript which we write in the notation of refractive index. See, the ray of light is coming from medium 1. So you will first write number 1, and it is going to, the ray of light is going to medium 2. So then you will write medium 2. So I want to um, uh, reframe my sentence, my statement, which I said. This means refractive index of medium 2 with respect to medium 1. The refractive index of medium 2 with respect to medium 1. Here again I would want to change the statement. Here it should be refractive index of medium 2 with respect to medium 1. What is medium 2? Medium 2 is the medium in which the ray of light is entering, and medium 1 is the ray of from which the ray of light is coming, right? So the ray of light is coming from air and entering into water. So air is medium 1 and water is medium 2. So the the first law of refraction states that the sine of angle of incidence, the ratio of sine of angle of incidence to the sine of angle of refraction is always constant, and it is known as refractive index of medium 2 with respect to medium 1. Always remember, it is the refractive index, the ratio of sine of angle of incidence to the sine of angle of refraction is the refractive index of medium 2 with respect to medium 1. Okay. Now, this number, this refractive index is a pure number. Note this down also. Refractive index of any medium with respect to any medium is a pure number. It has no units because it is a ratio of two similar quantities. It is the ratio of two similar quantities, and that's why it has got no units, right? Refractive index is a pure number. Okay, so refractive index, what does it tell actually? This number, if we see this number, what does it tell? See, I'll tell you. If refractive index is equal to 1, it means that, okay, before I write what does it imply, let me tell you what is the symbol. The symbol which I am making over here is the symbol of refractive index, which is a Greek letter mu, MEW, not meow. Okay, it's mu, Greek letter mu. Okay, so that's the symbol of refractive index. So if refractive index is 1, it means that speed of light does not change when a ray of light enters from one transparent medium to the other. When the ray of light enters from one transparent medium to other, the speed of light does not change, and that is the meaning of refractive index being 1. Now, understanding it further, it means that refractive index is 1 implies that sine of angle of incidence upon sine of angle of refraction is also 1, and that means this implies that sine of angle of incidence is equal to sine of angle of refraction, which in turn implies that angle of incidence is equal to angle of refraction. And that can never be the case if refraction is taking place, because in refraction the ray of light should bend. If the angle of incidence is equal to the angle of refraction, then how come the ray of light is bending? The ray of light is not bending. So you understand now, रिफ्रैक्टिव इंडेक्स 1 का मतलब होता है कि रिफ्रैक्शन हो ही नहीं रहा है। मतलब ये जो रे ऑफ लाइट है वो एक मीडियम से दूसरे मीडियम में भले जा रही है, लेकिन वो बेंड नहीं हो रही है। एंगल ऑफ इंसिडेंस और एंगल ऑफ रिफ्रैक्शन सेम है। अब बेंड नहीं हो रही है, इसका क्या मतलब है? इट मीन्स that the speed of light in both the media is the same. So both the media have same refractive index. ठीक है? ओके, लेट मी नॉट कंफ्यूज यू फर्दर विद दिस। सिर्फ याद रखना, म्यू अगर अगर इक्वल टू 1 है, इसका मतलब है स्पीड ऑफ लाइट डज नॉट चेंज व्हेन अ रे ऑफ लाइट एंटर्स फ्रॉम वन ट्रांसपेरेंट मीडियम टू अनदर. बट व्हाट if the refractive index is smaller than 1? It implies that sine I upon sine R is smaller than 1, which implies that sine of angle of incidence is smaller than sine of angle of refraction, which implies that angle of incidence is smaller than angle of refraction. Angle of incidence smaller than angle of refraction. When does this happen? Angle of incidence smaller than angle of refraction. Let me show you. See the second case. In this second case, what is happening? See the angle of incidence. See the angle of refraction. Is angle of incidence smaller than angle of refraction? Yes. So in this case, we can say that when we get this case, when the refractive index is smaller than 1, we can simply say that what we had written here, speed of light does not change. Okay, yeah, so we can say that speed of light increases when a ray of light enters a medium with refractive index smaller than 1. When a ray of light enters a medium with refractive index smaller than 1, its speed will increase. Right now, if you notice or if you study refractive index in detail, you will understand that there are no objects whose refractive index is smaller than 1, except one. That is no object, that is vacuum. Okay, so only vacuum has a refractive index slightly smaller than 1, slightly smaller. Okay, other than that, all the you can say, oh, I think I'm extremely wrong over here. Vacuum has refractive index equal to 1. Okay, the example over here is vacuum. Refractive index smaller than 1 is not possible. This example for this is not possible. Because you know why? Because in vacuum the speed of light has maximum value. So there is no other medium in which the speed of light is more than the speed of light in vacuum. Okay, so this is not possible. This case is absolutely not possible. Okay, what is the next case? The next case is that if refractive index is greater than 1. So when the refractive index is greater than 1, it means that sine I upon sine r is greater than 1. It means that sine I is greater than sine r, which in turn means that angle of incidence is greater than angle of refraction, and which generally happens when the ray of light enters from uh, rarer medium to denser medium, right? So we can say that speed of light decreases when the refractive index is greater than 1. We can say that when a ray of light enters a medium with refractive index greater than 1, its speed will decrease. Its speed will decrease. Okay, so these are, you can say, implications of uh, the value of refractive index. Correct? Okay, so let's now understand more meanings of this refractive index, more ideas regarding this refractive index. Okay, so I'm giving you some important notes over here. I hope you are noting it down, everything. Okay, let's understand refractive index in a new meaning. Refractive index, it is basically the ratio of sine of angle of incidence upon sine of angle of refraction, sine I upon sine r, and it tells us about its value, tells us about how fast or slow the speed of light will be in particular medium. Can also be calculated with the help of this new formula. Speed of light in medium 1 upon speed of light in medium 2. Speed of light in medium 1 upon speed of light in medium 2. Let me just confirm that with the textbook, because again we are having this medium 1 and 2. So I will get the diagram and will understand with the help of diagram what is this formula actually intending to tell us. Okay, so here we have this diagram. The ray of light is entering from air to water, that is medium 1 to medium 2. So when we write this formula, that the refractive index is speed of light in medium 1 upon speed of light in medium 2, the notation which we write over here, very important notation which we write over here, is 1 and 2. Always remember, 1 is the medium. 1 is the medium from which the ray of light is coming, and 2 is the medium in which the ray of light is entering. 2 is the final medium, 1 is the initial medium. So refractive, now how to tell this? While we say this, the meaning of this, while we speak, we say that refractive index of medium 2 with respect to medium 1. Refractive index of medium 2 with respect to medium 1. Okay. Refractive index of medium 2 with respect to medium 1 is speed of light in medium 1 upon speed of light in medium 2. So whenever we speak about refractive index, we always focus on the second number. This refractive index is of the second medium. Second medium here is water. Okay, in the previous definition or formula of refractive index also it is the same case, right? This is the previous definition we talked about. So here also I'm talking about refractive index of the second medium, which is water. So refractive index of water is sin I upon sin R, where water is the second medium, right? And refractive index of water or the second medium is speed of light in medium 1 upon speed of light in medium 2, or speed of light in air upon or vacuum or upon speed of light in water. So we have two formulae for refractive index now. Let me write both the formulae and give you a final idea about what we are studying. Okay, so refractive index of medium 2 with respect to medium 1. Can you tell me the ray of light is coming from which medium and going to which medium? Yes, it is coming from medium 1 and going to medium 2, क्योंकि 1 पहले लिखा है 2 बाद में लिखा है, ठीक है, ये तो क्लियर होना चाहिए. So refractive index of medium 1 with respect to medium 2 is equal to sine of angle of incidence in medium 1 upon sine of angle of refraction in medium 2, and it is also equal to speed of light in medium 1 upon speed of light in medium 2. Clear? This is refractive index of second medium with respect to the first medium. ठीक है, अब एक ट्रिक क्वेश्चन पूछता हूं, लेट्स से कितने लोगों को आता है. ठीक है, नाउ अपने आप को आंसर करो, मैं तुम्हें आंसर दूंगा तब कंफर्म कर लेना. ठीक है, कैन यू टेल मी व्हाट इज द रिफ्रैक्टिव इंडेक्स ऑफ मीडियम 1 विथ रिस्पेक्ट टू मीडियम 2? What is the refractive index of medium 1 with respect to medium 2? अब रे ऑफ लाइट कहां से कहां जा रही है? रे ऑफ लाइट जा रही है मीडियम 2 से मीडियम 1 में. ठीक है, तो यहाँ पे क्या हो जाएगा, साइन आर अपॉन साइन आई. अब जो एंगल ऑफ इंसिडेंस था वो एंगल ऑफ रिफ्रैक्शन बन गया, और एंगल ऑफ रिफ्रैक्शन जो था वो एंगल ऑफ इंसिडेंस बन गया. ठीक है, एंड ऊपर क्या आएगा, स्पीड ऑफ लाइट इन मीडियम 2 अपॉन स्पीड ऑफ लाइट इन मीडियम 1. ठीक है, तो ये हमेशा याद रखना कि हमको किसका रिफ्रैक्टिव इंडेक्स ढूंढना है. रिफ्रैक्टिव इंडेक्स हम हमेशा सेकंड मीडियम का ढूंढते हैं, मतलब जो इसके ये जो सेकंड नंबर होता है उसका ढूंढते हैं हम लोग रिफ्रैक्टिव इंडेक्स. ठीक है, अब हम एग्जांपल के साथ इसको समझेंगे और ये कॉन्सेप्ट को हम लोग फाइनल कर देंगे. ठीक है, तो इसका एग्जांपल मैं यहाँ पे तुम्हें नीचे देता हूं. चलो यही वाला एग्जांपल कंटिन्यू करते हैं. चलो, can you tell me what is the refractive index of water with respect to air? Refractive index of water with respect to air is sine of angle of incidence, which is formed in air, upon sine of angle of refraction, which is formed in water. It is also equal to speed of light in air or vacuum, which is just C, or if you want you can write CV or CA. C subscript V or C subscript A means speed of light in air upon speed of light in water. ठीक है, तो ये केस में हम लोग ये वाला जो फॉर्मूला है वो कंसिडर करेंगे टू फाइंड द रिफ्रैक्टिव इंडेक्स. किसका रिफ्रैक्टिव इंडेक्स ढूंढ रहे हैं हम लोग? सेकेंड मीडियम का विथ रिस्पेक्ट टू द फर्स्ट मीडियम. वी आर फाइंडिंग द रिफ्रैक्टिव इंडेक्स ऑफ सेकेंड मीडियम with respect to the first medium. ठीक है, ऑलवेज रिमेंबर दैट. और यहाँ पे सेकेंड मीडियम है कौन सा, जिसमें रे ऑफ लाइट एंटर कर रही है? कौन से मीडियम में एंटर कर रही है? वाटर में. ठीक है, अब लेट मी टेक द अदर एग्जांपल, द सेकेंड वन. ठीक है, सेकेंड एग्जांपल में we know that the speed the ray of light is entering from water to air. The ray of light is entering from water to air. So what refractive index can we find? We can find the refractive index of air with respect to water, because it is entering from water to air. Okay? And what will it be? It will be sine of angle of incidence upon sine of angle of refraction. See, the sine of angle of incidence is here and the sine of angle of refraction is here. Okay? And it is also equal to the speed of light in water upon speed of light in air. अब समझ में आया कैसे रिफ्रैक्टिव इंडेक्स ढूंढना है हमें? ठीक है, कोई भी केस है हम लोग रिफ्रैक्टिव इंडेक्स ढूंढ सकते हैं. ये दो फॉर्मूला है इसके, याद रखना. रिफ्रैक्टिव इंडेक्स ऑफ फर्स्ट मीडियम और रिफ्रैक्टिव इंडेक्स ऑफ सेकंड मीडियम विथ रिस्पेक्ट टू फर्स्ट मीडियम. ठीक है, या रिफ्रैक्टिव इंडेक्स ऑफ वाटर विथ रिस्पेक्ट टू एयर, या रिफ्रैक्टिव इंडेक्स ऑफ एयर विथ रिस्पेक्ट टू वाटर. ठीक है, चलो अब आई विल टेल यू अबाउट वन मोर अमेजिंग कॉन्सेप्ट जो रिफ्रैक्टिव इंडेक्स के जो सेकंड फॉर्मूला है उसको पूरी तरीके से जस्टिफाई करता है. एंड वी ऑल्सो गेट टू नो द रिफ्रैक्टिव इंडाइसेस ऑफ certain medium, certain transparent mediums which we are going to consider. Chalo. So the next topic which I want to discuss with you is absolute refractive index. ठीक है, absolute refractive index. ठीक है, absolute refractive index क्या है? Refractive index of any medium with respect to air or vacuum is known as its absolute refractive index. Refractive index of any medium with respect to air or vacuum is known as its absolute refractive index. Right? It also means one more thing. It means that ray of light is entering from vacuum or air to a given medium. ठीक है, इसका मतलब क्या है एब्सोल्यूट रिफ्रैक्टिव इंडेक्स का? कि रे ऑफ लाइट किसी मतलब एयर या वैक्यूम से किसी मीडियम में एंटर कर रही है, तभी हम एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ढूंढ सकते हैं. हाँ, तो अगर तुम बोलोगे कि जो पहले वाला एग्जांपल था ये तो एब्सोल्यूट रिफ्रैक्टिव इंडेक्स हो गया क्योंकि रे ऑफ लाइट एयर से वाटर में एंटर कर रही है, एंड यू आर एब्सोल्युटली करेक्ट. हाँ, ये एब्सोल्यूट रिफ्रैक्टिव इंडेक्स है. ठीक है, अच्छा इसका सिंबल क्या होता है? मैं सिंबल के एग्जांपल देता हूं. एग्जांपल्स. एब्सोल्यूट रिफ्रैक्टिव इंडेक्स मतलब आई एम सॉरी म्यू जी का मतलब क्या होता है? एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ऑफ ग्लास. एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ऑफ ग्लास. ठीक है, इसके बाद आता है म्यू डब्ल्यू. क्या है? एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ऑफ वाटर. एंड लास्ट में मैं लिखूंगा जो कंट्रोवर्शियल है, इसको लास्ट में हम लोग देखेंगे, म्यू ए विच इज एब्सोल्यूट refractive index of air. Absolute refractive index of air. अच्छा, यहां पे तुम नोट कर रहे हो मैंने सेकेंड मीडियम तो लिखा है, मतलब रे ऑफ लाइट ग्लास में आ रहा है, एंटर कर रहा है, वाटर में एंटर कर रहा है, एयर में एंटर कर रहा है. ये अलग अलग केसेस, मैंने 3 केस लिए. लेकिन ये कहाँ से आ रहा है वो नहीं लिखा है, मतलब फर्स्ट मीडियम कौन सा है, लेकिन वो लिखने की जरूरत नहीं है ना, क्योंकि हमें पता है कि रे ऑफ लाइट इज एंटरिंग फ्रॉम वैक्यूम और एयर, मतलब आ तो वो वैक्यूम या एयर से ही रहा है। ठीक है, अभी इसकी वैल्यू क्या होगी ये निकाल लेते हैं। ठीक है, तो इसकी वैल्यू के लिए अब जो मैं फॉर्मूला यूज करूंगा वो देखना तुम्हें समझ में आ जाएगा तुरंत। सो एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ऑफ ग्लास इज स्पीड ऑफ लाइट इन एयर और वैक्यूम, ठीक है, अपॉन स्पीड ऑफ लाइट इन ग्लास, स्पीड ऑफ लाइट इन एयर और वैक्यूम अपॉन स्पीड ऑफ लाइट इन ग्लास। ठीक है, तो कितनी है स्पीड ऑफ लाइट इन एयर या वैक्यूम? इट इज 3 × 10⁸ मीटर पर सेकेंड। And what is the speed of light in glass? It is approximately 2 × 10⁸ मीटर पर सेकेंड। तुम बोलोगे सर कैसे पता चला, आपने मेजर किया था क्या? नहीं नहीं नहीं, ये दीज आर ऑल कांस्टेंट वैल्यूज, तो इसकी अप्रोक्सीमेट वैल्यू हमें पता है, तुम्हें याद रखनी है। ठीक है, अच्छा इसको अगर कैलकुलेट करें 10⁸ 10⁸ कट मीटर पर सेकेंड कट 3/2 मतलब कितना आएगा 1.5। सो व्हाट इज द एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ऑफ ग्लास? 1.5। तुम्हें पता है इसका मीनिंग क्या है? यू नो इट्स मीनिंग, आई विल टेल यू इट्स मीनिंग। It means that it means that speed of light in glass is 1.5 times less than speed of light in air or vacuum. Speed of light in glass is 1.5 times less than speed of light in air or vacuum. मतलब जब ray of light एयर से या वैक्यूम से ग्लास में एंटर करती है तो उसकी स्पीड 1.5 टाइम्स कम हो जाती है। ठीक है, तो बताओ कौन अब ऑप्टिकली डेंसर है और कौन ऑप्टिकली रेयर है? ऑप्टिकली डेंसर ग्लास है एज कंपेयर टू एयर, क्योंकि उसका रिफ्रैक्टिव इंडेक्स ज्यादा है। ग्लास का एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ज्यादा है, मतलब वो ऑप्टिकली डेंसर है, मतलब जिसका रिफ्रैक्टिव इंडेक्स ज्यादा वो ऑप्टिकली डेंसर है। उसमें जब भी कोई रे ऑफ लाइट एंटर करेगी तो स्लो हो जाएगी और टूवर्ड्स नॉर्मल बेंड हो जाएगी। ठीक है, कितना सब कुछ कनेक्टेड है और क्लैरिटी हमें मिल रही है, ये देखो। ठीक है, नेक्स्ट I want to tell you what is the absolute refractive index of water. It is nothing but speed of light in air और vacuum। See, speed of light in air और vacuum का सिंबल C है, तो CA नहीं लिखेंगे ना तो भी चलेगा, C लिखो सिर्फ तो भी चलेगा, अपॉन स्पीड ऑफ लाइट इन वाटर CW। C upon CW means speed of light in air upon speed of light in water, which is 3 × 10⁸ meter per second upon speed of light in water. Do you know what is speed of light in water? Let me tell you. It is 2.25 × 10⁸ meter per second. As you can see, the speed of light in water is slightly more than the speed of light in glass. Matlab water is optically rarer than glass. Okay, now everything will cut and you will get 3 upon 2.25, which is 300 upon 225, which is if you cut this you will get, so this is 4/3, which is approximately equal to 1.33. So that is the absolute refractive index of water. So it means that the speed of light, you can write this statement now, it means that speed of light in water is 1.33 times less than the speed of light in air. So whenever the ray of light enters from air to water, its speed decreases by 1.33 times. Correct? And finally, you must be wondering why I'm writing that. Finally, the absolute refractive index of air, which is speed of light in air or vacuum upon speed of light in air or vacuum, which is nothing but 1, right? 3 × 10⁸ upon 3 × 10⁸. That means that the speed of light in air does not change throughout when the light is traveling from air to air does not change, right? So the lowest refractive index is of air. Then all the other medium comes. Air, then water, then glass, then oil, then glycerine, then alcohol. All these transparent mediums, they have different refractive index. The least is of air or vacuum. Air is actually not 1.000 something something something, but you can say very close to 1. So air and vacuum has refractive index of 1. Refractive index smaller than 1 is not possible. That's what I told you earlier. Refractive index 1 is possible. The speed of light does not change when a light enters from one medium to another having refractive index 1, and refractive index smaller than 1 is not possible, and refractive index greater than 1 means the speed of light decrease in that medium. And this we have understood with the help of different example, and also this new formula which relates the refractive indices of particular medium with the speed of light, right? Okay, few more examples. So this is absolute refractive index. Whenever we talk about absolute refractive index, it is just to understand that whether the speed of light in that medium slows down to a greater extent or to a smaller extent. Okay, that is what absolute refractive index tells you. But on a broader sense, uh, we can always apply this formula of refractive index, this concept of refractive index, to find refractive refractive index of one medium with respect to medium 1 with respect to medium 2, medium 1 with respect to medium 2. Okay, now let's find we can say, well, let's not talk about air for a moment. Let's not talk about absolute refractive index for a moment. Let's now talk about refractive index of two transparent media other than air. Okay, so what do you mean by refractive index of glass with respect to water? It means that uh, the ray of light is entering from water to glass. Okay, and how to find its value? Its value is equal to the speed of light in water upon speed of light in glass. Simple. Now we are not concerned with that complicated process of finding the sine of the angle of incidence to the sine of angle of refraction. Let's not go there. Let's focus on this formula, which is easier because we know the values of these constants. So speed of light in water is 2.25 into 10 raised to 8 and meter per second, and speed of light in glass is 3 into 10 raised to 8. So this will be 225 upon 300 if we simplify this. So we can simplify this further. 15 15s are, and 15 20s are, 5 3s are, 5 4s are. This will become 3 by 4 or 0.75. There you go, refractive index of glass with respect to water. Let's find the refractive index of water with respect to glass. And that will be speed of light in glass upon speed of light in water. Okay, so we had just simplified this expression here. So we can now say that refractive index of water with respect to glass will be 4 by 3, right? 4 by 3 or 1.33. Hey, is it 1.33? One second. I made a mistake. I made a mistake. It is my mistake. Let me correct myself, please. Here I made a mistake. It should be 2. It should be 2. And here the whole thing is incorrect. So let me write it again. It will be 2.25 upon 2 or 225 upon 200, not 300, because 3 into 10 raised to 8 is the speed of light in glass. So this is uh, this can be cut with the help of let's say um, 45 fives are, yeah, but 45 does not cut 200, so let's cut with 5. 5 fours are 20, and 5 5s are 25, and 5 40s are 5 9s are, and 5 8s are. Yes, so we get 9 by 8. Refractive index of glass with respect to water is 9 by 8. So can you tell me what will be refractive index of water with respect to glass? It will be 8 by 9, right? So generally we say that the refractive index of glass with respect to water is 1 upon, is the reciprocal of refractive index of water with respect to glass. And this is a very important, you can say, observation, which we can, very important relation which we have created, and we can generalize this relation now. This relation can be generalized and can be written as this. We can say that, therefore, we can say that refractive index of one medium with respect to uh, refractive index of medium 1 with respect to medium 2 is equal to 1 upon refractive index of 2 with respect refractive index of medium 2 with respect to medium 1, right? And we can also say that this implies that refractive index of medium 1 with respect to medium 2 multiplied by refractive index of medium 2 with respect to medium 1 is equal to 1, is equal to 1. This is a very, very important relationship which we have derived. ये सब डेरिवेशन किया है हमने, ऐसे ही मान नहीं लिया है, टेक्स्ट बुक में लिखा है इसके लिए, बट हमने फॉर्मूला डाल के वी हैव डिराइव्ड दिस रिलेशनशिप्स, राइट? अच्छा, इससे और एक चीज प्रूव होती है जो हम लोग अभी करने वाले हैं. See, we started from absolute refractive index. Now we are actually relating the refractive index indices of different media, and from this we can do one experiment. Let me get a figure for you, and then let's understand this experiment. Okay, so since we have understood this particular relationship between the refractive indices of two medium with respect to each other, we know that refractive index of medium uh, 1 with respect to medium 2 is the reciprocal of refractive index of medium 2 with respect to medium 1, or the product of refractive indices of uh, uh, medium 1 with respect to medium 2 and medium 2 with respect to medium 1 is equal to 1. Now we can understand the principle of reversibility. So what is this principle of reversibility? The principle of reversibility of light states that the path of a ray of light is reversible. According to this principle, if a ray of light travels from A to B, A to B means medium 1, from medium 1 to medium 2, along a certain path, it will follow exactly the same path while traveling from B to A, while returning from medium 2 to medium 1. So see here, the ray of light is entering from air into water, air to, now it is entering to water. Okay, let me use a darker shade. Okay, so it has bent. But if somehow you would put a mirror over here, you would put a mirror in water such that the ray of light strikes the mirror normally, perpendicularly, then it would reflect back along the same path. Now the reflected ray in water has become the incident ray, and it would follow the same path when it exits into air and travel along the same line, along the same path through which it entered initially. This is mathematically proven by this formula. This formula proves the principle of reversibility of light. It states that when a ray of light enters from one transparent medium to the second transparent medium, and when it travels from second transparent medium to the first transparent medium, in both the cases it follows the same path. Correct? So that is one thing I wanted to discuss with you. Now let's talk about one you can say practical aspect of refraction, that is refraction through a rectangular glass slab. So a rectangular glass slab, let me show you how does it look like. A rectangular glass slab looks like this. It's a normal glass slab, transparent glass slab. But how can we understand refraction better with the help of rectangular glass slab? That's what we want to understand. Okay, now see this. So the practical aspect of refraction. Here you can see a rectangular glass slab. Let me show you the incident ray. So this is the incident ray, PQ. O is the point of incidence. N is the first normal at the point of incidence. I is the angle of refraction. Now since the ray of light is entering from rarer medium air to denser medium glass, it will bend towards the normal. See, this is the refracted ray which is evidently bending towards the normal. Now this refracted ray will not just vanish. It will reach the other end of the rectangular glass slab at point O dash. At point O dash, it will emerge out of the rectangular glass slab, and this ray which emerges out is known as emergent ray, the ray which comes out of the rectangular glass slab. Okay, so this is the angle of incidence, this is the angle of refraction, this is also angle of refraction over here, because you see both the normals which are drawn at the point of incidence and the point of emergence, both these normals mn and m1n1 are parallel to each other. So this angle of refraction and this angle of refractions are forming alternate interior angles, so both are equal. This is the angle of emergence, which has been given symbol phi, but you can give it symbol e, angle of emergence. Okay, so this is emergent ray. Now the peculiar part in this whole experiment is that uh, there is a lateral shift which can be observed very easily in this whole thing, in between the incident ray and emergent ray. The incident ray and emergent ray have been laterally shifted. If you see the path of incident ray and the path of emergent ray, they are absolutely parallel to each other. So the ray of light has not overall bent, but it has laterally shifted. The ray of light has not overall bent, but it has laterally shifted. It has been laterally shifted. Laterally shifted means it has shifted from its position parallelly. Okay. So how does that happen? This happens because of these two parallel sides AB and CD of the transparent glass slab. Because of the parallel sides of the transparent glass slabs, what happens is the incident ray of light, when exits from the other side of the rectangular glass slab, uh, it emerges out as an emergent ray, which is parallel to the original direction of incident ray. So that's why there is a lateral shift. So definitely there has been a change of speed when the ray of light enters from air to glass, and again the speed has increased when the ray of light enters from glass to air on emerging out. But this has not resulted into permanent bending of light. This has resulted into a lateral shift. Okay, so this experiment has been written in your textbook in a greater detail, and you can use this experiment to find the refractive index of glass by finding the angle of incidence I and the angle of refraction R, and then sin I upon sin R will give you the refractive index of glass. The whole thing is explained, but for theoretical point of view, for your examination point of view, for writing your exam paper, the practical details are not required, but you must understand what is happening over here. So the whole experiment, it comes down to one single point, that is lateral shift. Now this lateral shift depends upon certain factors. Lateral shift depends upon, number one, the angle of incidence. Greater the angle of incidence, greater will be the lateral shift. Okay, greater the angle of incidence, greater will be the lateral shift. Second thing it depends on is the refractive index, the refractive index of the glass slab. Higher the refractive index of glass slab, greater will be the lateral shift. Greater the refractive index of material of the glass slab used, greater will be the lateral shift. Third thing it depends on is the or color or wavelength of light. Color or wavelength of light. If the wavelength of light is greater, that means lateral shift will be smaller. If the wavelength of light is smaller, then the lateral shift will be greater. Okay, how is this possible, and what are the colors for which the wavelength of light are different? That I will let you know now. Okay, so our next idea is to understand the color and wavelength of light. Let's go there. Okay, do you see this image? Now I will tell you what wavelength is. You have already studied wavelength in class 9, but I will tell you all over again. So wavelength is the distance between two consecutive crests or two consecutive troughs. So this is wavelength or this is wavelength. Okay, wavelength symbol is lambda. Now, if I draw few waves, suppose this is let me draw a bigger wave. You can see the waves here, but still I'd like to draw and ask you. So suppose this is the first wave and the second wave is like this. Which has got a greater wavelength? Here, this one has got a greater wavelength. Lambda is greater. This has got a smaller wavelength, very small lambda. So lambda is smaller over here. The symbol for wavelength is lambda. Okay. So as you can see in the visible light, which is made up of 7 constituent colors, which is VIBGYOR, not violent, violet, indigo, blue, green, yellow, orange, and red. Violet has got violet has got least wavelength, and red has got maximum wavelength. Okay, so just imagine that you are passing a red light into this glass slab. What will happen? I told you that the lateral shift depends on the wavelength. If the wavelength is more, for example, red light, if the red light is entering the glass slab, what will happen? The lateral displacement will be less. The lateral displacement will be less. And let's say if a violet or blue light enters the glass, then the lateral shift will be more, right? So with the color or wavelength of incident light, also this lateral shift depends upon. If the wavelength is more, lateral shift will be less. If the wavelength is less, then the lateral shift will be more. Okay, so these are the factors on which this lateral shift depends when a refraction through a rectangular glass slab takes place. Okay, now let's go to the next topic, which is multiple reflections. Just a moment. Okay, so multiple reflections of light and multiple images on multiple reflections of light through a thick mirror. So for that you need to understand that suppose your eye is over here. You have observed multiple reflections of light many times in your real life. You know, there are some changing rooms in which mirrors are placed parallel to each other, so you see so many images of yourself in those particular rooms, multiple images of yourself. So that is known as multiple reflections of light. Okay, so when a thick mirror is placed in front of yourself, when a thick mirror is placed in front of yourself, and there is an object, let's suppose that the object is a candle. Okay, and when you are looking at the image of the candle, what is happening? Now, why we are studying this particular topic here in refraction? Because there are many things which are taking place over here. If you see that certain rays of light which are coming from the candle are refracting and reflecting multiple times and forming multiple images of this candle, we have to study these images of candle and this multiple reflections and refractions which are taking place. Okay, so the let's say that one of the ray of the light from candle is going straight, like normally it's incident normally to the surface of the mirror, and it is reflected in the same direction, so that does not count. But when we produce this ray backward, we get the positions of the images, we get the line in which all the images are formed, which will be seen by us. Our eye is over here, we are the observer, we are over here. The other ray of light which is coming from candle, which concerns us and our position of the eye, is this OA. So this first ray strikes the mirror at this point and gets refracted. Before getting refracted, the reflection of it is it is occurring towards the path DB, and it reaches our eye. But you know what? The most of the light, it enters and goes inside. Suppose 100% of light is coming from the candle, 90% of it goes inside. Only 10% of it reflects back and comes to our eye. This 90% light, refracted light, hits point C and gets reflected back without diminishing its energy, gets reflected back and reaches this point. There is no name for this point, I will name it as point E. Reaches this point E and refracts back along path. Okay, there is already point E, let me make it point P, and refracts back along the path PE. Okay, and you can say that out of 90, around 84% of light is reflected back. Okay, remaining out of 90, 84% goes out towards your eye, remaining 6% is reflected inside, and then this multiple reflection and refraction keeps on happening, right? So this was 10% of brightness, this was 84% of brightness. Now the remaining brightness will be lesser than 10%, lesser than 6% in fact. Okay, maybe this is 5%, 4%, 3%, 1%, and so on. So what is happening? This second ray of light is the brightest. And where does the second ray of light go? If you produce it backward, it goes to the second image, I2. So the I2 image is the brightest image. Always remember, when multiple reflections and refractions of light take place through a thick mirror, the second image formed is the brightest. तुम जब ऐसे चेंजिंग रूम में जाते हो, तो चेंजिंग रूम में जो तुम्हें सेकंड इमेज दिखती है हमेशा सबसे ब्राइट रहेगी, फर्स्ट इमेज भी ब्राइट नहीं होती है इतनी जितनी सेकंड इमेज होती है. So this is one small part which we have just interesting part which they have taught in the last part. Okay, so इसके ऊपर इतना हमें डिस्कशन करने की जरूरत नहीं है. हाँ, इसको समझना है, बट मैथमेटिकल कोई डिस्कशन इसके ऊपर नहीं होगा. So there is, yeah, one small part which I have not discussed, which I want to discuss right now, is the effect of speed, wavelength, and frequency due to refraction of light and factors affecting the refractive index of a medium. Let's understand this in detail. So effect on speed, wavelength and frequency due to refraction of light. How does speed of light, wavelength of light and frequency of light change due to refraction of light? See, first thing, when a ray of light gets refracted from rarer to denser medium, the speed of light decreases. While if it is refracted from denser to rarer medium, the speed of light increases. Okay, so we know now how the speed is affected due to refraction. Frequency. See, the frequency of light depends on the source of light, so it does not change on refraction. Frequency depends on source of light. Frequency does not change on refraction. If v is the speed of light in a medium and lambda is the wavelength of the light in that medium, the frequency of light is given as v by lambda. Frequency is v by lambda. So v increases or decreases according to what lambda increases or decreases. But the ratio v by lambda always remains constant. Okay. Okay. When light passes from rarer medium to a denser medium, the wavelength of light decreases. Rarer to denser medium, the light becomes slower, so its wavelength decreases since the speed of light decreases. But its frequency remains unchanged. When the light passes from denser medium to rarer medium, the speed of light and hence its wavelength increases. Okay, so speed of light and wavelength, they behave in the same way. If the speed increases when ray of light passes from denser to rarer medium, wavelength also increases. If the speed decreases when the ray of light passes from rarer to denser medium, wavelength also decreases. Okay, here they have given one relationship of refractive index of a medium where when the light enters sorry, they have given the new wavelength, the formula for new wavelength of ray of light when it enters from one medium to another medium. So this formula, it simply states that the new wavelength, what is the new wavelength here? Lambda dash equals to the original wavelength in medium 1 upon refractive index of that medium in which the ray of light is entering. Okay, so I'm not going deeper into it. We'll come to it when some numericals based on this particular formula is given to us. Okay, let's go to the next topic, which is factors affecting refractive index of a medium. So refractive index of a medium depends on the following three factors: nature of the medium, that is its optical density. If the optical density is higher, uh, the refractive index of that medium is higher and the speed of that light in that medium will be less. If the optical density of the medium is little less, then the refractive index will also be less and the speed of light will be more. So smaller the speed of light, greater the refractive index. Greater the speed of light, smaller the refractive index. This we have discussed before also. Physical conditions as temperature, they also affect the refractive index of the medium. With increase in temperature, the speed of light in medium also increases, so the refractive index of the medium decreases. So if temperature increases, speed of light in that medium increases and the refractive medium decreases. And the third is color or wavelength of light, which we have just seen. Right, I've just shown you the color, how does the color or wavelength of light let me get, yeah, let me get, copy this image right next to the topic which we are studying. Okay, so what are they saying? The speed of light for all colors is the same in air or vacuum, but in any other transparent medium the speed of light is different for different colors. See, in air, all these colors travel with the same speed, that is 3 into 10 raised to 8 meter per second. Because you know, white light is made up of 7 constituent colors. So all the colors travel with the same speed in air or vacuum. But if they happen to enter air or water or glass, then for every color the speed of light is different in that particular medium. The speed of light is maximum for red color and speed of light is minimum for blue color, right? So we can say that for red light, let's speak about red light. For red light, the refractive index of a medium, the refractive index for a medium, if a red light is entering it, is always less. And for blue light, for violet or blue light, the refractive index of that medium will always be high. So we can say that for a given medium, the refractive index of violet light is always greater than the refractive index of red light for a given medium, for a given medium. Because that in that medium, when violet light enters or blue light enters, it travels slower. And when red light enters, it travels faster. So the refractive index should be higher for violet light and should be smaller for red light for a given medium. Okay, so these are few more I can say relations which I have given you. Now see, the whole first part is done with multiple reflections and everything. Now there are certain examples and questions, but I cannot give you any homework as of now because your test is approaching. So I will be making, you can say, more videos on this particular topic as well as the chapter. Now the next part is prism, so I'm going to cover prism first, and then I think the after prism the next part which I have to cover is simple applications of refraction of light, which is like apparent depth and everything. Mm, yes, so I think this chapter has got three parts in it. Okay, four parts. So critical angle is also there. So yeah, I will try to cover all the parts before your exam, because I have to teach everything in detail. So I'm not sure that how fast will I be able to cover those videos. But I'm trying my best to cover all the topics, because you see, if we don't do these solved examples and all, then it does not make any sense to cover the whole topic like how they are doing in their school. I cannot teach like that. Still, I'm not satisfied with today's lecture. It is more than 2 hours now. I think so. Yeah, close. We are close to 2 hours, but still, I want to, teach this topic in much more detail, which the time is not allowing us, which is a sad part. It should not happen. If this is the content given to you, then we should have all the time which we require for understanding this topic. But it's okay. We have started with the topic, and I'm going to cover the rest of the topic as soon as possible. So just watch this video, take notes. Homework I will give after your exams. I will share with you. But till then, just watch these videos, and if you have any doubts, just let me know. Okay. So see you in the next video. Bye bye.